All right. So that's our deal. We're talking about the atoms today. So, what's an atom?
Isn't everything made from atoms?
Everything is made from atoms, right? And things are made of matter, right? So atoms are matter, yeah? Um, you can take any material and cut it in half, right? And then then you can ask the question, what if you just kept taking that material and cutting it in half again, right? Is there a point at which you could not cut that material in half anymore? Okay, so that question has been asked for just literally thousands of years, right? So that's what we're going to get to. So the definition, what we like as the definition of an atom is it's the smallest part of an element that retains all the properties of that element. Elements are what we find on the periodic table, right? The periodic table to all of your right on the wall back there, that is showing us all of the matter that we know about. Okay, each little box on that table is a different kind of element, and it behaves chemically different from other ones, nearby it, or other ones in general. An atom is one piece of an element, right? I can hold a rock of uranium, right? But that rock of uranium is just made of many, many, many small pieces of uranium, right? And in principle, we can keep on cutting that rock in half until we get down to one single atom of uranium. So the smallest part of an element that retains all the properties of that specific element. That would mean if we took that element and we chopped it up, right? We take an atom and we chop it up, yeah? It's not going to act like itself anymore. It's not going to act like it did. You take an atom and separate electrons and protons, right? And then they're going to behave differently than the atom did as a whole, right? Smallest part of an element that retains the properties of that element. So here, let me give you just a brief history of how this goes. There's roughly 6 important events in the discovery of atoms, and I want you to kind of focus on when these happened. Okay, I'm not going to test you on this, but I want you to just get a feel for when these happened and see how interesting it is that the time, the spread of time between these events is set up in an interesting way. See if you can figure it out. So we start off with the ancient Greeks, and so it really does go back that far. Okay. We've had modern science, microscopes, telescopes, all that stuff for several hundred years, but we haven't had these things for thousands of years, okay? The ancient Greeks basically just had what they could, all their inquiry about the world was just done with their senses, right? Sight, sound, taste, touch, and smell. So it probably wouldn't surprise you that they basically considered the world to be made of only a few things. Let's see if I can make this happen right. Oh, dang it. So let me give all of this, because I can't make it pop up individually. So they basically thought the world was made up of only a few things. Earth, wind, water, air, and fire. Okay? Because if you're an ancient Greek without a microscope and no scientific techniques, right? You look around you and what do you see? You see some earth, you feel some wind, right? So that's the idea, right? Earth, wind, water, air, and fire. This stuff is circa roughly 500 to 300 BC. You notice how the times go backward. It starts at 500, goes to 300 because we are before year 0 in this case. So we're 2,500 years ago or so, okay, with the ancient Greeks. 3 important people: Leucippus, Democritus, and Epicurus. And this is sort of in order, okay, from first person to last person. They called themselves atomists. Okay. Now, in Greek, the word atom means without a cut or uncuttable. Okay. You know that because you know medical terms right now. You know a at the prefix of a word means without, right? Tome is a cut, right? So atome or atom means uncuttable or without a cut, without the ability to cut it. So yeah, they did exactly what I was saying, right? They looked around, saw that the earth was made out of stuff, and went, that stuff must be made of pieces, kind of like Legos, right? Now they knew they couldn't see those individual pieces because they probably tried, right? But it must be the case, right? Things have to be made of parts, right? They did not think that you would be able to continually keep cutting a rock in half and forever, right? They thought there must be a point at which it would stop. And they called that point an atom. They knew nothing about it except for that in principle, they thought it had to be there. Okay, so this is just sitting around basically hypothesizing about the world, going, this is what we think is going to be the case. Turns out they were right. They were right in the wrong way, but they were right. Yeah, they were right about atoms. They were just wrong in that there's only 5 substances. Okay, so Those are your three people. That's 2,500 years ago. Okay, we didn't come up with a new, fresh idea until the 1800s, right? So it took 2,000 years or so for us to come up with a new idea about what the world's made of. Okay, and this has to do with inventions at the time, microscopes, scientific methods, things like that. Okay, so you fast forward all the way to 1803. Someone named John Dalton. John Dalton has an idea about atoms. He classifies atoms by mass. He figures out there must be something called an atom. They actually just took the term from the ancient Greeks. They knew about ancient Greek philosophy and stuff, so they took the term. And they called the thing that they're describing an atom. At this point, we don't know what it looks like. We don't know how it's organized, right? So the whole goal of the 1800s and on is to figure out, all right, we have a thing called an atom. We know matter's made of stuff, right? And so let's figure out how it acts, what it looks like in air quotes, right? And so his idea was that basically matter was made of solid chunks, solid pieces that hooked together, okay, kind of like Velcro. Okay, you could hook all those pieces of matter together, and they held together. We now know there's bonds, electric and magnetic bonds between atoms, right, holding them together. But his idea was basically it was just hook and eye, right? Hook and eye is what Velcro is. Like there's a loop and there's a hook, and the little pieces hook together, right? Okay, and he also said things like elements composed of identical atoms would react in the same way. So now he has an idea that, take two of the same substance and they're going to behave the same, right? So now there's some consistency about atoms. Fast forward to 1869, so no big discoveries that were, worthy of putting on this for the next, 60-something years. And you get fast forward to somebody named Dmitri Mendeleev. Mendeleev is the one that you can credit for the periodic table. He built that first periodic table and made the modifications to it to get the current one that we have. He arranged atoms in order of increasing mass, designing the first periodic table because of that. And our modern table is very similar in that way. All of those atoms are arranged into rows and columns, and they behave in special ways. We're going to talk about the periodic table today. Okay, that's 1869. So you're noticing the times are getting shorter now. We went from 2,500 years ago to 1,800, and then we only went forward 60-something years to the next discovery, right? So now we're going to start going much faster, okay, with our discoveries. Fast forward to somebody named J.J. Thomson, 1904, okay? To give you perspective, we did not have even the beginnings of quantum mechanics yet. Einstein doesn't come up with his theories of the photoelectric effect or even relativity until 1905. So we're still like pre-Einstein. J.J. Thomson, I got to put all these up here. J.J. Thomson comes up with a model of an atom he calls the plum pudding model. Okay, plum pudding is raisin bread. For those of you who've never heard of plum pudding before, if you've been around physics for long enough, you've figured out what plum pudding is by now. But it's a term we we use all the time to describe the early thoughts we had about atoms. He imagined that atoms, what do we know at this point? We had electricity, we had magnetism. A person named James Clerk Maxwell discovered, or gave us a theory of electromagnetism in like the mid-1800s. So we knew about this. We've had electricity, magnetism for a long time. We knew about positive charges, we knew about negative charges, okay? And we knew that atoms must be comprised of these combinations of these positive and negative charges, electric charges, okay? So Thomson goes, all right, well, if atoms have to be positive and negative charges, how are they arranged within the atom? And so his idea was that basically it was just a big bag of particles, okay, like this, right? You had a bag, right, a sack, roughly speaking, filled with positive and negative charges, and he called it the plum pudding model. They call it plum pudding because, plum pudding is raisin bread, and so you can imagine there's like the bread with the raisins, which are the particles all spread out in the bread. Okay, that's why they call it the plum pudding model. So plum pudding is not an actual pudding. So in the plum pudding, the electrons are negative, the plums are raisins, and then the pudding is just a positive charge. Okay, and that was Thomson's idea. Turns out he was wrong, but he got something right. He got right that there were equal positive and negative charges, That was an important step. So even when we get things wrong in science, and this is the deal, right? Science is self-correcting. So even when we get things wrong, we might have some degree of like correctness to it, and we just keep that, and then we move on and we correct the wrong stuff. Fast forward only a few years to somebody named Ernest Rutherford. Rutherford gives us the model of the atom that puts the nucleus in the center. Okay, places the nucleus in the center. Nucleus has a positive charge, and electrons, I forgot that note apparently, but electrons orbit the nucleus, and they're negatively charged. So he keeps basically what Thomson said. We've got positive and negative electric charges in atoms, but he just rearranges them. He rearranges them not just because he wanted to. He actually does a test. He does an experiment and shows that it must be the case. I'll talk a little bit about that experiment in a little while. But let me just give you the rough picture of what Rutherford gives us. Rutherford tells us there's an atom, and the atom is made of a dense nucleus in the center, orbited by electrons. There were obvious problems with this immediately. He immediately does his experiment, comes up with his results, and goes, this can't be completely right. Okay? He was right about something. He was right about the dense nucleus. He was unfortunately wrong about the way electrons orbit. Okay? He pictured the electrons orbiting, basically whizzing around the atom, kind of like planets move around the solar system. Okay? But let me see if you guys can get this. What do we know happens when electrons move? What did we talk about happening when an electron goes from, I don't want to stand on this chair, but when an electron goes from a high orbital position to a low orbital position, what happens? What does the electron do?
It's knocked out.
It gains, well no, it loses potential and emits, so when I fall off of this chair, so I'm in a high orbital position, right, me as a human, and I fall off of the chair, I exchange potential energy for kinetic energy, right? Well, remember we said electrons have potential energy when they're in a high orbit, right? And when they drop to a lower orbit, which is moving, they lose potential, but they don't like gain kinetic energy. They emit electromagnetic energy, right? So where I fall down and make boom on the ground, right? Electrons fall down to their lower orbits and emit a photon of light, okay? So when electrons are moving, they must emit photons, okay? Rutherford knows that. After 1905, when Einstein gives us the photoelectric effect, Rutherford would have known this, okay? So he goes, this cannot possibly be right because in his model, electrons just orbited. They were whizzing around the nucleus, and we know when electrons move, they radiate photons. When they radiate photons, they lose energy. So you can do a calculation. If an electron is orbiting an atom, the nucleus of an atom, it must be radiating photons. If it's radiating photons, it must be losing energy. So you can ask, how long until an atom's electrons lose enough energy to where they just spiral into the nucleus and disappear, okay? And the answer is like milliseconds, okay? So if Rutherford was right, all atoms should be unstable and there should be no atoms, okay? So he knew immediately he couldn't be completely right, but he had to have something right, okay? Turns out he was right about the dense nucleus and wrong about the way electrons orbited, okay? So then you fast forward just a couple of years to somebody named Niels Bohr. Niels Bohr is one of the grandfathers of quantum physics. Him and Einstein and Schrodinger and a few other people are the ones who developed quantum physics. Bohr's one of his main contributions was to arrange the electrons. And his was, interestingly, not by experiment. He was completely a theorist. Rutherford was an experimentalist. Niels Bohr was a theorist, and he basically just proposed an idea. He said, what if the electrons don't just randomly orbit, at any distance? What if the electrons are stuck in specific orbits, right? So you have an inner orbit, and then a small distance from that, a next orbital, okay? And another distance from that, another orbital. And what if the electrons couldn't exist between orbitals? What if they had to jump from one to the next? okay? Meaning that the energy in the orbitals was quantized. You had to, if you wanted to get an electron from one orbit to the next one up, you had to put a specific amount of energy into it, okay? And if it wanted to go from one orbital, high orbital, down to a lower one, it had to lose a specific amount of energy, okay? The orbits were quantized, and it was just a guess, okay? Turns out it was right, okay? Right to some extent. Again, all these guys were right to some extent. So Bohr's modification was place the nucleus in the center like Rutherford does, but only allow the electrons to exist in specific orbits. These orbits represented different energy levels for the electrons, kind of like me standing on a chair, right? I stand on the floor, I have some energy. I stand on the chair, I've got more energy, right? I stand on a ladder, and I've got more energy, right? I can stand on discrete positions from the floor, right? It's honestly better to talk about a ladder, right? I can stand on one rung or the next rung up, right? I can't stand between the rungs, okay? That's how Bohr pictured atoms, as the electrons having to exist on one rung or another, right? An inner orbit, next orbit out, or the orbit from that. They couldn't exist anywhere between those orbits, okay? Interestingly, that also explains Einstein's photoelectric effect that he came up with in 1905 that I won't spend much at all time on, but it's nice when you, in physics, propose some idea and that idea explains another idea, okay? Then you know you're kind of on to something, okay? So this was Bohr's idea. It's called the Bohr's model of an atom. So when you see electrons arranged in specific shells, that's Bohr's model, okay? I'm gonna talk about one more person. That person's name is Erwin Schrödinger, and his discovery is 1926, okay? 1927, they put the finishing, polishing touches on quantum mechanics, so this is well into quantum mechanics. And Schrödinger, and I won't talk much about this, and you might have to just go Google some words if you want to know more, but Schrödinger says that atoms are not dense nuclei with orbiting electrons, but atoms are something called wave functions. They're kind of wavy. They're not dense particles. They're kind of waves and particles. And that was really where quantum mechanics got its feet on the ground. Schrödinger's equation. Turns out Schrödinger's equation matched up perfectly with Bohr's ideas, which matched up perfectly with Einstein's ideas, and then they were off to the races figuring out what the world was actually about. So let me show you what the idea is for atoms as a wave function. The idea is, and I know this looks a little confusing, the idea is that there are no point particle electrons. Their electrons aren't a little tennis ball orbiting a thing, okay? The electrons are a wave that can take up all of this space, okay? The space shown as all these colors here, okay? But basically the electron can be anywhere in this space. Where it is exactly is hard to say, okay? But it can be anywhere within this wave function, this volume of space around the atom, okay? And it's in none of these spots until it's measured. That's a little bit about how quantum mechanics works. I won't say more than that because we don't need it, okay? So that was 1926, Schrödinger. For radiography, everything we need to know about radiography, we're going to use Bohr's model of the atom. Okay, so we don't need to know about or even worry about atoms as this thing called a wave function. Okay, don't worry about it. So we stop at Bohr. I just want to make sure you know that it's gone on beyond him. Okay, and we haven't really done much since then. Okay, so from 1927, almost 100 years ago, we have not modified our view of how atoms act and look. Okay. All right, so now I'm going to jump over to my next, to the notes that I sent you guys. So that was just brief history, giving you some context so we can, understand this stuff a little better as we go into it.